Consider a single particle of light leaving the surface of the sun. It crosses the vast emptiness between that star and our planet, slips through the upper atmosphere, and finally lands in the lens of a telescope or the back of a human eye. To anyone watching from the outside, that trip takes time. It can be measured, predicted, and confirmed with instruments accurate to a tiny fraction of a second. The journey is real, and its duration is something physicists settled long ago. And yet there is a stranger truth hidden beneath that simple description. From the point of view of the light itself, if such a point of view can even be said to exist, no time passes at all. The departure from the sun and the arrival here are not separated by any interval the light could register. They are, in a sense, the equations make precise the same moment. This is not a trick of language or a poetic flourish. It falls directly out of the most thoroughly tested framework in all of physics, the theory that reshaped our understanding of space, time, and motion more than a century ago. The conclusion is so quietly radical that it tends to slip past even people who have studied the subject for years. Over the course of this exploration, we will build that conclusion from the ground up, starting with a single peculiar fact about light that refused to behave the way anyone expected. We will follow the reasoning carefully, step by step, until the timeless nature of light stops sounding impossible and starts sounding inevitable. The question is where that reasoning finally leaves us. The peculiar fact at the center of everything begins with a measurement that should have been simple and turned out to be the most stubborn number in physics. When you measure how fast light moves, you get a specific value, roughly 300,000 kilometers in every second. That figure by itself is not the surprising part. Plenty of things in nature have fixed speeds under fixed conditions. Sound travels through dry air at a particular rate that depends on temperature and pressure. A wave crossing the ocean moves at a pace set by the depth of the water and the pull of gravity. None of those speeds caused anyone to lose sleep because they all behaved the way ordinary motion is supposed to behave. They added and subtracted with the motion of whatever was doing the measuring. To see what that means, picture yourself standing on a railway platform as a train rolls past. Suppose someone on that train throws a ball forward in the same direction the train is moving. From the thrower's perspective, the ball leaves their hand at some modest speed. But from your perspective on the platform, the ball's moving faster because the speed of the train gets added to the speed of the throw. If the train moves at 50 kilometers an hour and the ball is thrown forward at 20, you on the platform see the ball travel at 70. Throw it backward instead, against the train's motion, and you would see it move at 30, the difference between the two speeds. This is the common sense arithmetic of velocities, and for most of human history, it seemed beyond question. Speeds simply pile on top of one another or cancel one another out depending on direction. Every measurement anyone had ever made agreed. Now, replace the thrown ball with a beam of light, mount a lamp on the front of that same train, and switch it on. The train is racing forward, so by the logic that worked so flawlessly for the ball, the light from the lamp ought to leave the train and reach you on the platform at its normal speed, plus the speed of the train. And if the train somehow reached an enormous fraction of light's own velocity, the beam streaming off the front should arrive carrying nearly twice the usual figure. That is what the arithmetic demands. That is what anyone reasoning from ordinary experience would predict with complete confidence. It is also wrong. When you actually measure the speed of that light from the platform, you get the same value you would have measured if the train had been sitting still. Not slightly more, not nearly double, exactly the same. The motion of the source adds nothing. And the strangeness does not stop there, because the effect is symmetric in a way that defies intuition entirely. Suppose you climb aboard the train yourself and chase after a beam of light that is already traveling ahead of you. You accelerate until you are moving at a tremendous speed in pursuit. Common sense insists that the light should now appear to be pulling away from you more slowly, the way a car ahead of you on the highway seems to drift away gently when you speed up to match its pace. The gap should close, the relative speed should shrink. But it does not. No matter how hard you chase, the light ahead of you recedes at exactly its full speed, as though you had never moved at all. Sprint toward an oncoming beam instead, closing the distance as fast as you can, and again the result refuses to budge. The light approaches you at precisely the same rate it would have if you stood perfectly still. This is the fact that broke physics open. Light does not play by the rules of addition and subtraction that govern every thrown ball, every rolling train, every other moving thing in ordinary life. Its speed is not measured relative to its source, and it is not measured relative to the observer. It is simply the same for everyone, everywhere, regardless of how anyone involved happens to be moving. Two observers racing toward each other at unimaginable speeds and a third drifting lazily in the opposite direction will all train their instruments on the same passing beam and all write down the identical number. There is no privileged vantage point from which light moves faster or slower. The value is locked. It is worth pausing to feel how deeply this violates expectation, because the discomfort it produces is not a sign of confusion. It is the appropriate response of a mind built by a world where speeds add. Everything in your direct experience tells you that if you move toward something, it comes at you faster, and if you flee from it, it falls behind more gently. You have confirmed this 10,000 times without ever thinking about it. Every time you merged onto a road or caught a ball or watched two boats pass on a river. Light alone refuses to cooperate. It treats your motion as irrelevant. You can throw the entire machinery of your velocity at it, and it absorbs none of that, returning the same answer with a kind of indifference. For a long time, no one could even imagine this was the case, because no one could move fast enough or measure precisely enough to notice. The discrepancy only becomes obvious at speeds that are a serious fraction of light's own, and nothing in ordinary human life comes remotely close. A jet aircraft, a bullet, a planet hurtling around its star, all of these are crawling by comparison. At such gentle speeds, the old arithmetic of adding velocities works almost perfectly, because the error it introduces is far too small to detect. The cracks only show when the speeds involved grow enormous, and by then, the cracks are not small flaws but a complete collapse of the framework. The arithmetic does not bend a little under strain, it fails outright, and something entirely different takes its place. The natural reaction, the one that occupied some of the finest minds for decades, was to assume that the measurements must somehow be hiding an ordinary explanation. Surely light moved relative to something, even if that something was invisible and had never been directly observed. Surely there was a medium it traveled through, a substance filling all of space, and the constant speed was simply light speed through that substance. If that were true, then by measuring how light speed appeared to change as our own planet moved through the medium, we could detect our motion against the fixed background of the cosmos. The reasoning was sound. The expectation was reasonable. It fit everything known about every other kind of wave, all of which need a medium to travel through. Sound needs air. Ripples need water. Light, surely, needed something too. That assumption set up one of the most important experiments ever performed, an attempt to catch the Earth in the act of sliding through the invisible sea that light was thought to require. The result of that experiment would not merely fail to find what it sought, it would deepen the mystery to the point where the only way forward was to abandon assumptions that had seemed too obvious to question, including assumptions about the nature of time itself. But before we can appreciate why that experiment mattered so much, we have to understand how anyone first came to suspect that light had a finite speed at all, and how that suspicion turned a beam of light from something instantaneous into something that could be timed, measured, and ultimately understood. What, after all, made anyone think that light took any time to travel in the first place? For most of recorded history, the prevailing assumption was that light arrived everywhere at once. When you open your eyes in a dark room and a lamp is lit, the illumination seems to fill the space in the same instant the flame appears. There is no perceptible delay, no sense of the light creeping outward from the source to the walls. Many of the ancient thinkers who considered the matter concluded that light must be instantaneous, that its transmission across any distance took no time whatsoever. A few suspected otherwise, reasoning that anything that moves from one place to another should require some interval to do so, however brief. But suspicion is not measurement, and for a very long time, no one had any way to settle the question. The speed of light, if it had a speed at all, was simply too great to catch with the crude timing methods available. The first serious attempt to put a number on it was almost charmingly direct. The idea was to station two people on distant hilltops, each holding a lantern fitted with a shutter. The first person would uncover their lantern, and the moment the second person saw that light, they would uncover theirs in response. By measuring how long it took for the returning light to appear, and knowing the distance between the hills, one could, in principle, calculate how fast the light had traveled. It was a clever scheme in concept, but it was doomed by the very thing it was trying to measure. Light crosses the distance between two hilltops in a span far shorter than any human can react to. The entire delay in the experiment came from the reaction time of the people holding the lanterns, the lag between seeing a flash and moving a hand. The light itself contributed nothing measurable to the total. The experiment could establish only that light moved faster than human reflexes could track, which was not saying much. Whatever light speed was, it lay beyond the reach of lanterns on hills. The breakthrough, when it finally came, did not come from a faster shutter or a quicker observer. It came from looking up, away from the Earth entirely, toward a clock far larger and steadier than anything that could be built by hand. That clock was the system of moons orbiting the planet Jupiter. These moons circle their parent world on regular schedules, passing behind it and emerging again with the reliability of a well-made timepiece. Astronomers had charted their motions carefully and could predict well in advance exactly when a given moon should slip into Jupiter's shadow and exactly when it should reappear. The eclipses of those moons formed a celestial clock visible across enormous distances, and that turned out to be precisely what was needed. The crucial observation was that the predicted times of these eclipses did not hold steady through the year. They drifted. When the Earth, in its own orbit, was positioned closest to Jupiter, the eclipses ran ahead of schedule, arriving a little earlier than the tables said they should. When the Earth swung around to the far side of its orbit, placing it much farther from Jupiter, the same eclipses ran behind, arriving later than predicted. The pattern of the lag matched the changing distance between the two planets. When we were near, the news of each eclipse reached us promptly. When we were far, that news was delayed. The only sensible explanation was that the light carrying that news took time to cross the extra distance. The eclipses were not actually happening at different times. The light announcing them was simply arriving late when it had farther to travel. This was the decisive insight. By measuring how much the eclipse timings shifted over the course of the year and knowing roughly how much the distance between Earth and Jupiter changed, one could finally extract a value for the speed of light. The first estimate produced this way was rough by modern standards, off by a noticeable margin, because the distances involved were not yet known with precision. But the magnitude was right, and far more importantly, the conclusion was right. Light has a finite speed. It is enormous, almost incomprehensibly large by everyday standards, but it is not infinite. Light takes time to go places. The illumination that seems to fill a room instantly is in fact arriving after a journey, one too short to notice, but real all the same. Sunlight reaching the Earth is already several minutes old by the time it lands. Starlight is older still, sometimes by thousands or millions of years. The sky we see is a record of the past, layered by distance, each point of light showing us its source, not as it is, but as it was when that light departed. Once the finite speed of light was accepted, the problem shifted from whether light had a speed to measuring that speed with ever greater accuracy here on Earth, without relying on the motions of distant planets. The methods grew steadily more ingenious. One approach used a rapidly spinning toothed wheel placed in the path of a light beam. The beam passed through a gap between two teeth, traveled a long distance to a distant mirror, and reflected back toward the wheel. If the wheel was spinning at just the right rate, the returning beam would arrive exactly when a tooth had rotated into its path, blocking it so that the observer saw nothing. Speed the wheel up or slow it down slightly, and the beam would slip through the next gap and become visible again. By knowing the distance to the mirror, the number of teeth, and the rate of spin that caused the light to be blocked, one could calculate how long the round trip had taken, and from that, the speed of light. It was the lantern on the hill reborn with a mechanical observer fast enough to do the job, a spinning wheel that could react in a tiny fraction of the time any human hand ever could. Later, refinements replaced the toothed wheel with a rotating mirror, and then with still more precise arrangements, each pushing the measured value closer to its true figure. What emerged from all this effort was not just a number, but a growing sense that this number was special. It kept showing up. It was the same whether you measured light from the sun, light from a lamp, or light bounced off a distant mountain. It did not seem to depend on the color of the light or the nature of its source. The speed of light was beginning to look less like an incidental property of a particular phenomenon and more like a fundamental feature of the world, a constant woven into the fabric of things. But knowing that light had a fixed speed did not yet explain why it had that speed or what set the value. Why 300,000 kilometers a second and not 10 times more or 100 times less? The measurements could tell you how fast light moved, but they could not tell you why it moved at exactly that rate. For that, the answer would come not from timing beams across distances, but from an entirely different direction, from the study of electricity and magnetism, two forces that at first glance seemed to have nothing to do with light at all. The unification of those forces would reveal something astonishing about the nature of light, and in doing so, it would explain where that stubborn universal speed came from. What could a magnet and a spark possibly have to tell us about a ray of sunlight? The connection emerged through the careful study of two phenomena that had been known for centuries, but were long treated as separate curiosities. Electricity was the business of sparks and charges, of amber rubbed with cloth and the crackle of static, of the strange ability of certain materials to attract or repel one another after being handled in particular ways. Magnetism was the business of lodestones and compass needles, of the mysterious force that aligned a suspended sliver of iron with the direction of the earth, of the invisible reach that let one magnet tug at another across a gap. These two effects looked nothing alike. One involved charges that could be built up and discharged, the other involved a permanent pull locked into certain rocks and metals. For a long time, there was no reason to think they were related at all. The first hint of a deeper link came from a simple observation that an electric current flowing through a wire could deflect a nearby compass needle. The needle, which ordinarily pointed steadily along the Earth's magnetic direction, would swing aside when current ran through a wire placed near it and swing back when the current stopped. This was a small effect, easy to overlook, but its implication was profound. Electricity in motion produced magnetism. A flowing current was not merely an electrical thing, it generated a magnetic influence in the space around it, reaching out to push the compass needle off its usual heading. The two phenomena, electricity and magnetism, were touching each other through this experiment, revealing that they were somehow two aspects of a single underlying reality. The relationship turned out to run both ways. If a moving electric charge could create magnetism, then a changing magnetic field could in turn create electricity. Move a magnet near a coil of wire, and a current springs up in the wire, flowing as long as the magnet keeps moving and ceasing the moment it stops. This is the principle behind every electrical generator ever built, the reason that spinning a magnet inside coils of wire produces the power that flows through cities. Electricity makes magnetism, and changing magnetism makes electricity. The two are locked in a reciprocal dance, each capable of giving rise to the other. They were not separate forces that happened to interact. They were two faces of one force, which we now call the electromagnetic force, and the realization that they were unified was one of the great achievements in the history of science. The full mathematical description of this unified force was a set of equations that captured, with remarkable economy, every known fact about how electric and magnetic fields behave and how they generate one another. These equations described how charges produce electric fields, how currents produce magnetic fields, how a changing magnetic field induces an electric one, and how a changing electric field induces a magnetic one. Together, they formed a complete and self-consistent account of electromagnetism, and they were celebrated for their elegance and their power to predict. But buried inside them was something that no one had been looking for, a consequence that fell out of the mathematics almost as an accident and that would change everything. The equations implied that electric and magnetic fields could sustain one another in a kind of endless relay, even with no charges or currents present at all. Imagine a changing electric field. According to the equations, that changing electric field generates a magnetic field. But that newly created magnetic field is itself changing, growing as the electric field changes, and a changing magnetic field generates an electric field in turn. So the magnetic field gives rise to a new electric field, which is also changing, which generates another magnetic field, and on and on. Each field continually regenerates the other, and the whole interlocked pattern can propagate forward through empty space, a self-sustaining wave of electric and magnetic disturbance feeding on itself as it travels. Nothing needs to carry it. It carries itself, the two fields taking turns, creating each other as the wave moves outward. This was a startling prediction in its own right, the existence of waves made purely of electric and magnetic fields, rippling through space with no material medium required. But the truly remarkable part came when the equations were used to calculate how fast such a wave would travel. The speed was not a free parameter that could be anything at all. It was fixed by two specific quantities that appear in the equations, two numbers that describe how strongly electric and magnetic fields are produced in empty space. These two quantities had been measured independently, in experiments that had nothing to do with light, simply by studying the strength of electric and magnetic forces in the laboratory. When their measured values were plugged into the calculation for the speed of an electromagnetic wave, the result was a specific number. That number was the speed of light, not approximately, not coincidentally, but precisely the speed that had been so painstakingly measured by timing beams across distances and watching the eclipses of distant moons. The wave that the equations predicted, the self-sustaining ripple of electric and magnetic fields, traveled at exactly the speed of light because it was light. Light was revealed to be nothing other than an electromagnetic wave, a propagating disturbance in the electric and magnetic fields, the same fields responsible for sparks and compass needles and the current in a wire. The thing that illuminates the world and the thing that makes a magnet cling to a refrigerator were unmasked as expressions of one underlying phenomenon. The mystery of light's nature had been solved by the study of electricity and magnetism, two forces that had seemed to have nothing to do with it. This unification did far more than satisfy curiosity. It explained where light's stubborn universal speed came from. The speed was not an accident of how light happened to be produced. It was dictated by the fundamental properties of empty space itself, by those two quantities describing how readily space supports electric and magnetic fields. Light moved at its particular speed because the very structure of space and the nature of the electromagnetic force demanded it. Change the color of the light, change the source that produced it, and none of that touched the underlying speed, because the speed was set not by the light but by the medium of its existence, the electromagnetic field permeating all of space. It also opened up a vast hidden world. If light was an electromagnetic wave with a particular wavelength, then there was no reason waves could not exist with other wavelengths, longer or shorter than those the eye can see. And indeed they do. The light we see with our eyes occupies only a narrow band of a far larger spectrum of electromagnetic waves. Stretch the wavelength longer and you find the infrared radiation we feel is heat, then the microwaves that cook food and carry signals, then the radio waves that span the gaps between transmitters and receivers. Shrink the wavelength shorter than visible light and you find the ultraviolet that burns skin, then the energetic radiation used to image bones, then the still more energetic rays that pour from the most violent processes in the cosmos. All of these are the same kind of wave, differing only in wavelength, all of them traveling at exactly the same speed through empty space, the speed of light. The visible world is a thin slice of a much broader reality, and the equations had revealed the whole of it. But this beautiful picture carried a troubling implication that would not go away. The equations specified a single definite speed for electromagnetic waves. They did not say a speed relative to the source, or relative to the observer, or relative to anything in particular. They simply gave a number, fixed by the properties of space, and this raised an obvious and uncomfortable question. A speed must be measured relative to something. When we say a train moves at a certain speed, we mean relative to the ground. When we say a swimmer moves at a certain speed, we mean relative to the water. So when the equation said light moved at its particular speed, the natural question was, relative to what? What was the something against which light's speed was to be measured? The search for that something would lead to one of the most consequential experiments ever attempted, and to a result that no one wanted. What exactly was light supposed to be moving through? The answer that seemed obvious, the answer that nearly everyone accepted, was that light must travel through a medium that filled all of space, a substance so thin and so pervasive that it had never been directly detected, but that had to be there for light to move through. This hypothetical medium was given the name aether, and the reasoning behind it was difficult to argue with. Every other wave anyone had ever studied required a medium. Sound is a wave of compression traveling through air, and where there is no air, as in the vacuum of space, sound cannot travel at all. A wave on the surface of a pond is a disturbance in the water, and without the water, there is no wave. Waves were understood as disturbances in some material, oscillations passing through a substance, and it seemed inconceivable that a wave could exist without something to do the waving. If light was a wave, as the equations now firmly established, then there had to be a medium carrying it, even across the apparent emptiness between the stars. That medium was the ether, and it was thought to fill the entire universe, an invisible sea through which light rippled and through which all the planets and stars moved. The ether neatly answered the troubling question of what light's speed was measured relative to. Light moved at its fixed speed relative to the ether. The ether was the stationary background, the absolute frame of rest against which all motion could in principle be gauged. This was a deeply satisfying idea because it restored the ordinary common sense arithmetic of velocities that light had seemed to violate. If light moved at a fixed speed through the ether, then an observer moving through the ether should measure light's speed differently, depending on whether they were moving with the light or against it, exactly as the platform observer measured the thrown ball differently depending on the train's motion. The strange constancy of light's speed could be preserved as something that held true only relative to the ether, with moving observers seeing different values, just as intuition demanded. This had a thrilling consequence. If the ether was the fixed background of the universe, and if the Earth was moving through it as it orbited the Sun and as the Sun moved through the galaxy, then we ought to be able to detect that motion. The Earth would be sailing through the ether like a ship through a still sea, and that motion should produce a kind of ether wind, a flow of the medium past the Earth. Light traveling in the same direction as the Earth's motion through the ether should behave differently from light traveling across that motion or against it, because the ether wind would help or hinder the light just as a river current helps or hinders a swimmer. By measuring these differences with sufficient precision, we could determine how fast and in what direction the Earth was moving through the ether, and thereby establish our absolute motion against the fixed frame of the cosmos. This was an extraordinary prospect. It promised to reveal the Earth's true motion through the universe, measured against the unmoving ether itself. The experiment designed to detect this ether wind was a masterpiece of precision, and its logic was elegant. The idea was to send light on two journeys at once, one along the direction of the Earth's presumed motion through the ether, and one across that direction perpendicular to it. A beam of light was split into two, with one part sent down a path aligned with the Earth's motion and the other sent down a path at right angles to it. Each beam traveled out to a mirror, reflected, and came back. If the Earth was moving through the ether, the two beams should take slightly different amounts of time to complete their round trips, because one was fighting the ether wind on part of its journey while the other was crossing it. When the two beams were recombined after their trips, this difference in travel time would show up as a detectable shift in the pattern they made when their waves overlapped. The experiment was sensitive enough to detect even a tiny difference, far smaller than the effect the Earth's known orbital motion should produce. To understand why the two beams should differ, consider an analogy with a swimmer in a flowing river. Suppose a swimmer can move at a fixed speed through the water. If that swimmer swims a certain distance downstream and then back upstream to the starting point, the round trip takes a certain amount of time. The downstream leg is fast, helped by the current, but the upstream leg is slow, fighting against it, and the slow upstream portion costs more time than the fast downstream portion saves. Now, suppose the same swimmer instead swims across the river to a point directly opposite on the far bank and back. To go straight across against a current, the swimmer must angle slightly upstream to avoid being swept sideways, which costs some time, but the situation is symmetric on the return, and the total time for the across and back trip turns out to be different from the time for the downstream and back trip over the same distance. The two routes, one parallel to the current and one perpendicular to it, take different amounts of time. The light beams in the experiment were the swimmers, the ether wind was the current, and the difference in their travel times was what the experiment was built to detect. Everything was in place, the apparatus was sensitive, the logic was sound, the expectation was clear. The Earth was certainly moving, hurtling around the Sun at a substantial speed, and the Sun was moving through the galaxy as well, so there should have been a robust ether wind to detect. The two beams should have shown a difference. The experiment was performed with great care. The apparatus rotated to catch the ether wind from every angle. The measurements repeated to rule out error. The result was nothing. There was no difference between the two beams. No matter which way the apparatus was oriented, no matter how carefully the measurements were taken, the light behaved as though there were no ether wind at all, as though the Earth were standing perfectly still in the ether. The two beams, one supposedly fighting the ether current and one crossing it, returned in exactly the same time. The ether wind that should have been there was simply absent. The experiment, designed to measure the Earth's motion through the ether, found that motion to be zero, which was impossible, because the Earth was unquestionably moving. This was a genuine crisis. The result could not be easily dismissed, because the experiment was repeated and refined many times, always with the same null outcome. The ether wind was not faint or hard to detect. It was not there, and this left physics in an extremely awkward position. Either the Earth was not moving through the ether, which contradicted everything known about the Earth's orbit and the Sun's motion, or there was no ether at all, which seemed to leave light as a wave with nothing to wave in, an impossibility by the standards of the time. Various attempts were made to rescue the situation. Perhaps the Earth dragged the nearby ether along with it, so that locally there was no relative motion. But this idea ran into conflicts with other observations and grew increasingly contrived. Perhaps objects moving through the ether physically contracted along their direction of motion by just the right amount to hide the effect. This last idea was closer to the truth than its proposers realized, but as offered, it was an arbitrary patch with no deeper justification, a fudge inserted only to explain away an unwanted result. The experiment had delivered a clear verdict, and the verdict was that something fundamental was wrong with the entire framework. The constant speed of light was not constant only relative to some hidden medium. It was simply constant, full stop, for every observer regardless of motion, exactly as the equations had implied, and exactly as direct measurement confirmed. There was no ether, no fixed background, no absolute frame of rest against which light speed could be gauged. The question of what light moved relative to had been answered, and the answer was that the question itself was wrong. The resolution would require abandoning an assumption so deeply held that almost no one had thought to question it, an assumption not about light at all, but about the nature of time. What would it take to make the speed of light come out the same for everyone, no matter how they moved? The conventional response to a stubborn experimental result is to look for the flaw in the apparatus, the overlooked source of error, the hidden assumption in the measurement. For a long time, that is exactly what people did, proposing increasingly elaborate mechanisms to explain why the ether wind refused to appear while still preserving the ether itself. The genuinely radical move, the one that broke the deadlock, was to stop trying to save the ether and instead take the experimental result at absolute face value. The speed of light is the same for every observer, not because of some conspiracy of effects that happen to cancel out, not because the Earth drags a local pocket of ether along with it. but simply because that is how the universe is built. The constancy of light speed was promoted from a puzzle demanding explanation to a foundational principle requiring no explanation at all, a starting assumption from which everything else would follow. This was a profound shift in strategy. Rather than asking why light speed appeared constant, the new approach declared the constancy a law of nature, and then asked what the rest of physics must look like in order to be consistent with it. If the speed of light truly is identical for all observers, regardless of their motion, then something else has to give, because that constancy flatly contradicts the ordinary arithmetic of adding velocities. The question became, what are we willing to sacrifice to keep the speed of light constant? And the answer turned out to be the things that everyone had always assumed were absolute and unchanging, the very bedrock of common sense, namely the idea that time flows the same way for everyone, and the distances are fixed regardless of who measures them. To see why time and space had to give way, return to the central conflict. Speed is distance divided by time. If two observers moving relative to one another both measure the same beam of light and both get the same speed, but they are moving differently relative to that beam, then something about their measurements of distance and time must differ in a way that exactly compensates. There is no other possibility. If the speed comes out the same for both, and speed is built from distance and time, then their distances and times cannot both be the same. At least one of them must change, and as it happens, both do. The observer who is moving relative to the light measures distances and times that are subtly different from the observer at rest, and the differences are precisely what is needed to make the calculated speed of light come out identical for both. The constancy of light speed is purchased at the cost of the universality of space and time. This is the heart of the matter, and it is worth dwelling on because it overturns something so deeply ingrained that we rarely even notice we believe it. We assume, without ever examining the assumption, that time is universal. We assume that there is a single cosmic flow of time, the same everywhere, ticking forward at the same rate for everyone, so that the question of whether two events happened at the same moment has a single definite answer that all observers would agree on. We assume that an hour is an hour, here or on the far side of the galaxy, for someone sitting still or someone racing across the cosmos. We assume, equally, that space is universal, that the distance between 2 points is a fixed fact, the same for everyone who measures it, and that the length of an object is simply what it is, independent of who is observing it or how they are moving. These assumptions feel less like beliefs and more like the obvious structure of reality. They are so basic that questioning them seems almost meaningless. But these assumptions had never actually been tested at the speeds where they break down. They were generalizations from ordinary experience, from a world in which everything moves slowly compared to light. And in that slow world, the assumptions hold to extraordinary accuracy. The trouble is that they are not exactly true. They are approximations, excellent ones at low speeds that fail when speeds approach that of light. And the new approach, the one that took light's constancy as fundamental, forced exactly this conclusion. If light speed is the same for all observers, then time and distance cannot be universal. They must depend on the relative motion of the observer. Time must run at different rates for observers moving differently, and distances must measure differently as well. These are not optical illusions or errors of measurement. They are real changes in the actual intervals of time and space, dictated by the requirement that light speed remain constant. The principle was elevated alongside one other, equally important assumption, namely that the laws of physics are the same for all observers moving at constant velocity. This second principle says that there is no experiment you can perform entirely within a smoothly moving laboratory that would reveal your motion. If you are sealed inside a windowless cabin, moving at a perfectly steady speed in a straight line, everything inside behaves exactly as it would if you were at rest. A ball thrown straight up comes straight back down. Water poured from a pitcher falls naturally into a cup. There is no internal sign of your motion because constant velocity motion is, in a deep sense, indistinguishable from rest. This is why you do not feel the enormous speed of the Earth's orbit, and why a smooth flight at cruising altitude feels no different from sitting in an airport lounge. Motion at constant velocity is relative. There is no absolute standard of being at rest, no privileged frame against which true motion can be measured. This was precisely the death of the ether, which had claimed to provide exactly such a privileged frame. Put these two principles together, the constancy of light speed and the relativity of motion, and the entire structure of space and time reorganizes itself around them. The consequences are not minor adjustments, they are sweeping and strange, touching everything we thought we knew about duration and distance, and even the meaning of simultaneity, of whether two events happen at the same time. That last casualty deserves special attention because it is perhaps the most counterintuitive of all. If time is not universal, then the question of whether two distant events are simultaneous does not have a single answer. Two events that one observer judges to happen at the same instant may, for another observer moving differently, happen at clearly different times, one before the other. There is no fact of the matter about absolute simultaneity, no cosmic now that spreads across all of space. What counts as the present moment at a distant location depends on who is asking and how they are moving. The shared, universal present that we instinctively believe in simply does not exist. This is the price of taking light's constancy seriously, and it is a steep one. We must give up the universal flow of time, the fixed nature of distance, and the absolute meaning of now. In exchange, we get a framework that is perfectly consistent with every experiment ever performed, including the one that found no ether wind and that makes precise predictions confirmed to staggering accuracy. The framework does not merely tolerate the constancy of light, it is built upon it as a cornerstone, and everything else, all the strangeness of stretching time and shrinking distance, follows as a logical necessity. These are not separate weird effects bolted on to explain particular results. They are the unavoidable consequences of two simple principles worked out with care. Of all these consequences, the one most directly relevant to our central question is the way that motion affects the passage of time. If time runs at different rates for observers moving differently, then a clock in motion does not tick at the same rate as a clock at rest. This is the effect that will, when pushed to its limit, lead us to the timeless nature of light itself. But before we can follow it that far, we need to understand precisely how and why motion slows the passage of time, and we need to see that this is not vague philosophy, but a quantitative, measurable, repeatedly confirmed fact. How exactly does moving through space change the rate at which time passes? The slowing of time with motion is not a metaphor and not an approximation. It is a measured, demonstrated fact, confirmed by experiments precise enough to leave no room for doubt. A clock that is moving relative to you ticks more slowly than a clock at rest beside you. The faster it moves, the more slowly it ticks. This effect is utterly negligible at the speeds of ordinary life, which is why no one ever noticed it until they could measure with extreme precision or observe objects moving at enormous speeds. But it is real, and its reality has been established many times over in ways that leave the conclusion inescapable. One of the clearest demonstrations comes from particles produced high in the atmosphere when energetic radiation from space strikes the upper air. These collisions create certain unstable particles that survive only for a tiny, fixed span of time before they decay into other particles. The lifespan of these particles is well known from laboratory studies, where they can be created and watched as they decay. That lifespan is extraordinarily short. Knowing how fast these particles travel, which is very close to the speed of light, and knowing how long they live before decaying, one can calculate how far they should be able to travel before they vanish. The answer is a relatively short distance, far too short for them to reach the ground from the height where they are created. By the ordinary reckoning, almost all of them should decay high in the atmosphere, long before reaching the surface. Very few should ever make it down to where we could detect them, and yet they arrive at the surface in great numbers, far more than should survive the journey. The discrepancy is enormous, not a small excess, but an overwhelming one. The explanation is precisely the slowing of time with motion. From our perspective on the ground, these fast-moving particles have clocks that run slow. Their internal countdown to decay, which proceeds at a fixed rate when they are at rest, is stretched out because they are moving so quickly relative to us. Their brief lifespan, measured by our clocks, is extended enough that they can cross the distance to the surface before decaying. The particles last longer, as we measure their lasting, because their internal sense of time is dilated by their motion. The number that reach the ground matches the prediction of time dilation with precision. These particles are, in effect, natural clocks moving at nearly the speed of light, and they tick slow exactly as the framework demands. There is a beautiful symmetry hidden in this example that reveals how deep the effect goes. We described it from our perspective on the ground, where the particle's clock runs slow and its lifespan is stretched. But the principle of relativity insists that the particle's own perspective is equally valid. From the particle's point of view, it is at rest, and it is the Earth that is rushing up toward it at nearly the speed of light. From the particle's perspective, its own lifespan is perfectly normal, the same short span it always has. It does not experience any stretching of its own time. So how does it manage to reach the ground in its brief, unstretched life? The answer involves the other consequence of the framework, the shrinking of distance. From the particle's perspective, the distance it must travel to reach the ground is contracted, compressed to a fraction of what we on the ground measure. The atmosphere it must cross is squashed thin in its direction of motion. So the particle crosses a much shorter distance in its normal lifespan, while we see it cross the full distance in a stretched lifespan. Both perspectives are correct, and both arrive at the same conclusion that the particle reaches the ground. The two effects, time stretching and distance shrinking, are two sides of the same coin, and which one you invoke depends on whose perspective you adopt. The physics works out identically either way. This symmetry points to something essential. Time dilation is not a matter of one clock being truly fast and another truly slow. It is reciprocal. If you and I are moving relative to one another, I see your clock running slow, and you see my clock running slow, and we are both right, because there is no absolute standard of rest to break the tie. This sounds paradoxical, like it should produce a contradiction, but it does not, precisely because simultaneity is also relative. The apparent paradox dissolves when you account for the fact that we also disagree about which events are simultaneous. The full picture is perfectly consistent. There is no contradiction, only the unfamiliar consequence that time and simultaneity are not the shared universal things we instinctively believe them to be. The effect has been confirmed in more controlled settings as well. Extremely precise clocks, accurate enough to measure differences of billionths of a second, have been flown around the world aboard aircraft and compared with identical clocks left behind on the ground. After the journey, the clocks that traveled showed a different elapsed time than the clocks that stayed home, by an amount that matched the prediction. The flying clocks, having moved at high speed relative to the ground, had ticked slightly slow during their journey, and so recorded slightly less elapsed time than their stationary counterparts. The difference was tiny, as it must be at aircraft speeds, but it was real and measurable, and it agreed with the calculation. Time dilation is not confined to exotic particles in the upper atmosphere. It happens to ordinary clocks, to any clock whenever it moves. It happens to you when you walk across a room, though by an amount so small that no instrument could ever detect it. There is an additional subtlety worth mentioning because it deepens the picture. Motion is not the only thing that affects the rate at which time passes. Gravity does too. A clock deeper in a gravitational field, closer to a massive body, runs slow compared to a clock farther away. This is a separate effect from the slowing due to motion arising from a different part of the broader theory, but it is no less real. The clocks flown on aircraft were affected by both, by their motion, which slowed them, and by their higher altitude in the Earth's gravity, which sped them up relative to the ground, and the net result was the sum of these competing effects. The systems that let us navigate by satellite must account for both kinds of time distortion with great precision, because the satellites carrying the clocks are both moving fast and sitting high in the Earth's gravity. And if the resulting time differences were ignored, the navigation would drift into error within minutes and become useless within a day. The fact that satellite navigation works at all is a continuous practical confirmation that time runs at different rates depending on motion and gravity. Every time a position is fixed by satellite, the equations of relativity are being relied upon and confirmed. So the slowing of time with motion is established beyond reasonable doubt. It is not a theoretical curiosity, but a feature of the world, woven into the behavior of particles, clocks, and the navigation systems that guide travel across the planet. The faster something moves, the slower its time passes. As measured by an observer, it is moving relative to. And this immediately raises the question that drives us toward our destination. If time slows more and more as speed increases, what happens at the ultimate speed, the speed of light itself? If a clock moving at half the speed of light ticks noticeably slow, and a clock moving at nearly the full speed of light ticks dramatically slow, then what does a clock do when it actually reaches the speed of light? The trend is clear, but to understand where it leads, we need to look more carefully at exactly how the slowing depends on speed. And for that, there is no better tool than a remarkably simple thought experiment built from nothing more than a beam of light bouncing between two mirrors. What does that bouncing beam reveal about the nature of time itself? The thought experiment is deceptively simple, and that simplicity is its power. Imagine a clock built from light. Take two mirrors and mount them facing each other, one above the other with a small gap between them. Send a single pulse of light bouncing back and forth between them, reflecting off the top mirror, traveling down to the bottom mirror, reflecting again, traveling back up, and so on, endlessly. Each complete round trip of the light pulse, up and back down, counts as one tick of this clock. Because the speed of light is fixed and the distance between the mirrors is fixed, the time for each tick is perfectly regular. This is a real clock in every meaningful sense. It measures time by counting the bounces of a light pulse, and it does so with complete reliability. Such a clock is sometimes called a light clock, and it is the ideal instrument for thinking about time because its ticking is governed directly by the one quantity we know to be constant for everyone, the speed of light. Now, consider this light clock at rest beside you. The light pulse goes straight up and straight down, bouncing between the mirrors, and each round trip takes a definite amount of time, determined by the distance between the mirrors and the speed of light. The pulse travels twice the gap between the mirrors during each tick, once up and once down, and since it moves at the speed of light, the duration of a tick is simply that double distance divided by light speed. This is your clock, at rest, ticking away at its natural rate. Nothing unusual is happening. The light goes up and down along a straight vertical line, and the ticks come at regular intervals. Now, set this same clock in motion. Imagine it mounted on a vehicle that glides past you at high speed, moving horizontally while the light pulse still bounces vertically between the mirrors. Here is where the crucial insight emerges. From the perspective of someone riding along with the clock, nothing has changed. The light still goes straight up and straight down between the mirrors, bouncing as before, ticking at its normal rate. For the rider, the clock is at rest and it behaves exactly as it always did. But from your perspective, watching the clock fly past, the situation looks entirely different. Because the whole clock is moving horizontally while the light travels between the mirrors, the light pulse does not appear to go straight up and down. By the time the pulse reaches the top mirror, that mirror has moved forward, so the pulse has had to travel up and also forward to catch it. And by the time it returns to the bottom mirror, that mirror too has moved forward, so the pulse travels down and forward again. From your vantage point, the light pulse traces a zigzag path, a series of diagonal lines rather than a straight vertical line. The pulse is moving up and down as before, but it is also being carried along horizontally with the moving clock, and the combination of these two motions makes its path a diagonal one. This diagonal path is the key to everything. A diagonal line between 2 points is longer than a straight vertical line between them. The pulse, as you observe it, has to travel farther during each round trip than it would if the clock were at rest, because the diagonal zigzag covers more distance than the straight up and down path. The pulse climbs the same vertical gap, but it also covers horizontal ground, and so the total distance it travels along its diagonal route is greater. Now, here's the decisive point, the point on which the entire conclusion turns. The speed of light is constant. The pulse cannot travel its diagonal path any faster than it traveled its vertical path, because light always moves at exactly the same speed for every observer, including you. The speed does not increase to make up for the longer path. So if the pulse must cover a greater distance and it cannot do so any faster, then it must take more time to complete each round trip. Each tick of the moving clock, as you observe it, takes longer than each tick of the same clock at rest. This is time dilation, derived from nothing more than the constancy of the speed of light and a little geometry. The moving clock ticks slow, as you observe it, because its light pulse must travel a longer diagonal path while constrained to move at the same fixed speed. The faster the clock moves horizontally, the more stretched out the diagonal becomes, the longer the path the light must travel, and the more slowly the clock ticks from your perspective. There is nothing mysterious about the mechanism once you see it laid out this way. It follows inexorably from the fact that light speed is the same for everyone. If you accept that the light pulse always moves at the same speed regardless of how the clock is moving, then you are forced to conclude that the moving clock ticks slow because there is simply no other way for the geometry to work out. What makes this argument so compelling is that there is nothing special about a clock built from light. You might object that this is just a peculiarity of light clocks, that an ordinary clock made of gears or a spring or a vibrating crystal would not be affected. But that objection cannot stand, and the reason is the principle of relativity. Recall that the laws of physics must be the same for all observers moving at constant velocity, and that there is no experiment you can perform within a smoothly moving laboratory that would reveal your motion. Now, suppose you had a light clock and an ordinary mechanical clock sitting side by side, both at rest, ticking in perfect agreement. If you set both in motion and the light clock slowed down while the mechanical clock did not, then the two clocks would fall out of sync, and you could detect this disagreement from inside the moving laboratory. You would have found an experiment that reveals your motion, which is forbidden. Therefore, the mechanical clock must slow down by exactly the same amount as the light clock. And the same argument applies to every process that marks time, including the vibrations of atoms, the decay of unstable particles, the chemical reactions of metabolism, the firing of neurons, the aging of a living body. All of them must slow by precisely the same factor when in motion, because if any of them slowed differently from the others, that difference would betray the motion, in violation of the principle that constant velocity motion is undetectable from within. This is a profound generalization. It means that time dilation is not about clocks at all, not really. It is about time itself. When something moves, its time, all of its time, every process that unfolds within it, slows down as measured by an observer it is moving relative to. The moving thing does not experience this slowing. From its own perspective, everything proceeds at the normal rate, because its own clock and its own biological processes and its own thoughts all slow together in perfect lockstep, leaving no internal way to notice. It is only from the outside, from the perspective of an observer in relative motion, that the slowing appears. And it appears for every clock, every process, every measure of time, without exception. Time is the thing that slows, and the light clock is simply the clearest window onto that fact. The amount of slowing depends on the speed in a specific way that becomes important as we approach our destination. At low speeds, the diagonal path is barely longer than the vertical path, and the slowing is minuscule, far too small to notice. This is why ordinary experience never reveals the effect. But as the speed increases and approaches that of light, the diagonal becomes more and more stretched. The path the light must travel grows dramatically longer relative to the vertical gap, and the slowing becomes severe. The relationship is not gentle and linear. As the speed of the clock approaches the speed of light, the slowing accelerates, growing without limit. A clock moving at a modest fraction of light speed ticks only a little slow. A clock moving at a large fraction ticks dramatically slow, and a clock approaching the speed of light approaches a state where its ticks stretch toward infinite duration, where time, as observed from outside, grinds toward a halt. The trend that the bouncing light pulse reveals points clearly toward an extreme, and that extreme is reached precisely at the speed of light. If a moving clock ticks slower the faster it moves, with the slowing growing without bound as it nears light speed, what becomes of time at that ultimate limit? And what does the same motion do to the distances that observer measures? The same motion that stretches time also compresses space, and the two effects are bound together as inseparable aspects of a single phenomenon. Just as a moving clock ticks slow as observed from outside, a moving object is shortened along its direction of motion. As measured by an observer, it is moving relative to. This is not a squeezing or a physical crushing in the ordinary sense. Nothing presses on the object to compress it. The shortening is a genuine feature of how space itself is measured by different observers, a consequence of the same constancy of light speed that produces the slowing of time. An object racing past you is measured to be shorter along the direction it is traveling than it would be if it were at rest beside you. To understand why this must be so, it helps to return to the particle from the upper atmosphere and look at the situation from both perspectives once more, because the logic that forced time to stretch in one frame forces distance to shrink in the other. From our perspective on the ground, the fast-moving particle has a stretched lifespan due to time dilation, and so it crosses the full thickness of the atmosphere before decaying. But from the particle's own perspective, its lifespan is perfectly normal and unstretched. It does not experience any slowing of its own time. So in its brief, ordinary life, how does it manage to traverse the atmosphere? The only way the two perspectives can agree on the outcome, that the particle reaches the ground, is if the distance the particle must cross is, from its perspective, much shorter than the distance we measure from the ground. The thickness of the atmosphere, which we measure as substantial, is compressed in the particle's frame to a fraction of that thickness. The particle does not need a stretched lifespan because it does not have so far to travel. The distance has shrunk to match. This is the contraction of distance, and it is the necessary partner of time dilation. The two effects are not independent. They are coordinated so that all observers, regardless of their motion, agree on the physical outcomes of events even as they disagree about the individual measurements of time and space that lead to those outcomes. We on the ground explain the particle's arrival by saying its clock ran slow, so it lived long enough to cross the full distance. The particle explains its own arrival by saying the distance was short, so it crossed it in its normal lifespan. Both accounts are correct, both are required, and they are linked by the same factor that governs time dilation, so that the amount by which time stretches in one frame is precisely mirrored by the amount by which distance shrinks in the other. Whatever factor stretches the moving clock's ticks is the same factor that compresses the moving object's length. They are two expressions of one underlying relationship between space, time, and the constant speed of light. The contraction applies only along the direction of motion, not perpendicular to it. An object moving horizontally is shortened in the horizontal direction, but unchanged in its vertical and depth-wise dimensions. A sphere flying past at enormous speed would be measured not as a smaller sphere, but as a flattened shape, compressed along its line of travel while retaining its full extent across that line. This directional character is essential and follows from the same geometry that produced the diagonal light path in the moving clock. Motion singles out a particular direction, the direction of travel, and it is along that direction alone that distances are affected. Across the direction of motion, measurements are unchanged, which is why the vertical gap between the mirrors in the light clock stays the same for both observers, even as the horizontal motion stretches the light's path. Like time dilation, the contraction of distance is reciprocal, and this reciprocity is once again the source of much apparent paradox and its resolution. If you watch an object fly past, you measure it to be shortened along its direction of motion, but from the object's perspective, it is at rest, and it is you and everything around you that is flying past in the opposite direction, and so from the object's perspective, it is you who are shortened. Each observer measures the other to be contracted. There is no contradiction in this, just as there was none in each observer measuring the other's clock to run slow, because the resolution again lies in the relativity of simultaneity. To measure the length of a moving object, you must note the positions of its two ends at the same moment. And since observers in relative motion disagree about what counts as the same moment, they disagree about the lengths they measure. The disagreement is not an error. It is built into the structure of space and time. There is no single true length of a moving object, just as there is no single true rate at which a moving clock ticks. These quantities depend on the motion of the observer, and different observers will measure them differently, each correctly within their own frame. It is worth confronting how strange this is, because it strikes at another assumption we hold without examination. We believe that an object has a definite size, a length that belongs to it intrinsically, the same for everyone who measures it. A meter stick is a meter long, we think, and that is simply a fact about the stick. But this is not so. The length of the stick depends on its motion relative to the measurer. A stick at rest beside you has its full length. The same stick flying past you at high speed is measured to be shorter, and the faster it moves, the shorter it is measured to be. At speeds near that of light, the contraction becomes extreme, and the stick is measured to be a tiny fraction of its rest length, squashed toward a flat sheet along its direction of travel. The length that we naively imagine to be a fixed property of the object turns out to be a relationship between the object and the observer, mediated by their relative motion and the constancy of light's speed. This brings us once more to the limit, the question of what happens as the speed approaches that of light. Just as time dilation grows without bound as the speed nears light speed, with the moving clock's ticks stretching toward infinite duration, the contraction of distance grows toward an extreme as well. As the speed approaches that of light, the measured length of a moving object along its direction of travel shrinks toward zero. The object is compressed more and more, flattened thinner and thinner, until at the limit of light speed, its extent along the direction of motion would contract to nothing at all. And the distance such an object would traverse from its own perspective would likewise contract toward zero, so that an arbitrarily long journey through space would, in the object's frame, become arbitrarily short. The two limits work together. From the outside, the object's time slows toward a complete stop. From the object's perspective, the distances it crosses shrink toward nothing. These twin extremes, time stretching toward infinity from the outside and distance shrinking toward zero from within, are converging on something. They are pointing toward a particular state of affairs that would hold for anything actually moving at the speed of light, a state in which no time passes and no distance separates the start of a journey from its end. But before we can reach that conclusion cleanly, we need to look more carefully at what the framework says about the relationship between an object's speed and the rate at which its own time passes relative to ours, and we need to be precise about the difference between what we measure of a moving object and what that object measures of itself. The contraction of distance and the dilation of time are measurements made by observers in relative motion, and to understand light's own situation, we must learn to distinguish between the time we attribute to a moving thing and the time that thing carries with it as its own. How fast must something move before its own time nearly stops relative to ours, and what governs that internal clock it carries? The relationship between an object's speed and the slowing of its time is not gradual in the way our intuition might suggest. We might imagine that doubling the speed doubles the effect, or that the slowing creeps up steadily as the speed increases. But that is not how it works. At ordinary speeds, and even at speeds that seem tremendously fast by human standards, the slowing of time is so small as to be utterly undetectable. An object moving at 1,000th of the speed of light experiences almost no time dilation at all. Even at 1/10 of the speed of light, a speed at which an object would circle the entire Earth in a fraction of a second, the slowing of time is modest, a small percentage. The effect remains gentle across a wide range of speeds, which is part of why it eluded discovery for so long. You can go astonishingly fast and still have your time pass at very nearly the normal rate relative to an observer at rest. But as the speed climbs toward that of light, the character of the relationship changes dramatically. The slowing, which was gentle and gradual, begins to accelerate. As an object approaches the speed of light, its time dilation does not increase by a little more for each additional increment of speed. It increases by more and more, climbing steeply, then more steeply still, rising toward an extreme as the speed draws near to that of light. The closer the speed comes to light speed, the more violently the time dilation grows. An object moving at 90% of light speed has its time slowed by a noticeable factor. At 99%, the slowing is far more severe. At 99.9%, more severe still, and the trend continues without end. There is no speed just below that of light at which the time dilation levels off. Instead, it grows without limit, heading toward infinity precisely as the speed reaches that of light. The last tiny increments of speed, the final approach to light speed, produce enormous increases in the slowing of time, far out of proportion to the small gain in speed. This explains why the speed of light functions as an absolute limit, a barrier that no object with mass can ever reach, let alone cross. As an object is pushed faster and faster, approaching the speed of light, its time, as observed from outside, slows toward a stop, and at the same time, it becomes harder and harder to push the object any faster. The energy required to increase the speed grows without bound as the speed approaches that of light. To actually reach light speed would require infinite energy, which is to say, it cannot be done. The closer an object comes to light speed, the more its resistance to further acceleration grows, climbing toward infinity at the limit. No matter how much energy you pour into accelerating an object with mass, you can bring it closer and closer to the speed of light, but never actually reach it. The speed of light is an asymptote, a limit approached but never attained, for anything that has mass. This is not a practical limitation of engineering or available power. It is a fundamental feature of the structure of space and time. Mass simply cannot be accelerated to the speed of light, because doing so would demand infinite energy and would entail infinite time dilation, both of which are impossible to actually realize. To make sense of light's own situation, we need to draw a careful distinction between two different things that the word time can refer to in this context. There is the time that we, as outside observers, measure for a moving object, the time we attribute to it based on watching it move past us. This is the time that appears dilated, stretched out, when we observe a fast-moving clock ticking slowly. But there is also a different and more intrinsic notion of time, the time that the object itself carries with it, the time measured by a clock that travels along with the object, at rest relative to it. This is the time the object actually accumulates as it moves through the world, the time that governs its own internal processes, its own aging, its own sequence of experiences, if it is the kind of thing that has experiences. This intrinsic time, the time carried by an object along its own path, is a particularly important quantity, because unlike the time we measure for the object from outside, which depends on our motion relative to it, the object's own carried time is something more fundamental, a property of the path the object takes through space and time, independent of any particular outside observer. The distinction matters enormously. When we say a moving clock ticks slow, we are describing how its ticking appears to us, the outside observers. And we noted that this is reciprocal, that the clock would also see our clock ticking slow. There is no absolute fact about whose clock is really slower, because that depends on the relative motion and the relativity of simultaneity. But the time a clock accumulates along its own actual path through space and time is not reciprocal in this way. It is a definite quantity, the total amount of time that elapses for that clock as it travels from one event to another along a specific route. Two clocks that start together take different paths through space and time, and reunite will generally show different total elapsed times when they meet again, and there is a definite fact about which one shows more. The clock that took the path involving more motion, more speed, will have accumulated less of its own carried time. This is not a matter of perspective. When the clocks are brought back together and compared directly, the difference is plain and unambiguous. One has aged less than the other, and both agree on which. This carried time, the time an object accumulates along its own path, is the deepest and most physically meaningful notion of time for that object. It is what the object's own clock reads, what its own processes track, what its own aging measures. And it is precisely this carried time that we must examine for light, because the question of whether light experiences time is really the question of how much of this carried time a beam of light accumulates along its journey. We have established that as an object's speed approaches that of light, the time we measure for it from outside slows toward a stop, and the distances it traverses shrink towards zero from its own perspective. The carried time of an object, the time accumulated along its path, is intimately related to these effects. A fast-moving object accumulates less carried time than a slow one traveling between the same two events, because the carried time depends on the path through space and time in a way that penalizes high speed. The faster you go between two events, the less of your own time you accumulate getting there. This points clearly toward what must happen at the limit. If an object moving at high speed accumulates less carried time than one moving slowly, and if this reduction grows more severe as the speed approaches that of light, then an object moving exactly at the speed of light would accumulate the least carried time of all. The trend suggests that this least amount is, in fact, none at all, that a beam of light traveling between two events accumulates zero carried time along its path. But to establish this rigorously, rather than merely extrapolating a trend, we need a precise tool, a quantity that the framework provides for calculating exactly how much carried time accumulates along any path through space and time. That quantity is the same one that all observers agree upon, the single combined measure that unifies space and time into a coherent whole, and it is to this quantity that we must now turn. What is the actual measure that the universe uses to combine space and time into a single quantity, one that every observer, however they move, will agree upon? The resolution to all the apparent disagreements between observers lies in a single quantity that everyone, regardless of their motion, will measure to be the same. We have seen that observers in relative motion disagree about durations of time, that one observer's clock runs slow as measured by another. We have seen that they disagree about distances, that one observer's meter stick is contracted as measured by another. We have seen that they even disagree about simultaneity, about whether two events happen at the same time. With so much disagreement, it might seem that there is nothing solid left, nothing that all observers can agree upon, no objective bedrock beneath the shifting measurements of space and time. But there is such a bedrock, and finding it is the key to understanding the deep structure of reality that the framework reveals. The insight is that space and time, which we are accustomed to thinking of as separate and independent, are actually woven together into a single unified entity, a four-dimensional fabric in which the three dimensions of space and the one dimension of time are merged. This unified entity is called spacetime, and it is the true stage on which all events occur. The reason different observers disagree about space and time separately is that they are slicing this unified spacetime in different ways. Imagine a loaf of bread that can be sliced at different angles. One person slices it straight across, another slices it at a tilt, and they end up with differently shaped slices, even though the loaf itself is one fixed object. Similarly, different observers, moving differently, slice spacetime into space and time in different ways, and that is why their measurements of space and time taken separately do not agree. But the loaf itself, the underlying spacetime, is the same for everyone. The disagreements are about how it is sliced, not about what it is. Because space and time are unified in this way, there is a combined measure of the separation between two events that takes both their spatial separation and their temporal separation into account, and this combined measure is the same for all observers. It is called the space-time interval, and it is the quantity that everyone agrees upon. While observers disagree about how much time separates two events and how much distance separates them, when they combine these in the particular way the framework prescribes, they all arrive at the same value for the interval between those two events. The interval is the objective, observer-independent truth about the separation of two events, the thing that survives the shift from one observer's perspective to another's. It is the invariant quantity, invariant meaning unchanging across different observers, the solid bedrock beneath the relative and shifting measurements of space and time taken on their own. The way the interval combines space and time is the crucial and surprising part, because it does not combine them the way we combine ordinary spatial distances. If you want to find the straight line distance between 2 points in space, you combine their separations in the 3 spatial directions in a familiar way, and the more separation in any direction, the greater the total distance. Spatial separations all add together to increase the distance. But the space-time interval does not work like this. When combining the spatial separation and the temporal separation between 2 events, the framework subtracts rather than adds. The spatial separation and the temporal separation work against each other in the interval, the one tending to reduce the contribution of the other. This is the essential difference between time and space within the unified spacetime, the minus sign that distinguishes the time direction from the spatial directions. Time enters the interval with the opposite sign from space, and this single feature is responsible for nearly all the strange and characteristic behavior of relativity, including, as we will see, the timeless nature of light. This combined interval, with its subtraction of space against time, is directly related to the carried time we discussed, the time an object accumulates along its own path. For 2 events that occur at the same place in some observer's frame, with no spatial separation between them, the interval is just the time between them, and this is the carried time of a clock present at both events, ticking away in between. As spatial separation is introduced, as the 2 events grow farther apart in space, that spatial separation subtracts from the interval, reducing the amount of carried time between the events. This is the mathematical heart of why fast motion reduces carried time. A fast-moving object covers a lot of spatial distance between 2 events, and that large spatial separation subtracts heavily from the interval, leaving less carried time accumulated along the path. The faster the object moves between 2 events, the more spatial distance it covers, the more that distance subtracts, and the less carried time it accumulates. The carried time and the spatial distance traded against each other through this subtraction are 2 contributions to the single invariant interval. We can now see the relationships between all the effects we have discussed unified under this single quantity. Time dilation, the slowing of moving clocks, the contraction of moving lengths, the relativity of simultaneity. All of these are consequences of the fact that observers slice the unified spacetime differently while the underlying interval remains fixed. Each observer measures their own slices of space and time, and these slices differ, but they all describe the same spacetime, governed by the same invariant interval with its characteristic subtraction of space against time. The framework is not a collection of separate strange effects. It is a single coherent geometry, the geometry of spacetime, with the interval as its fundamental measure, and all the surprising consequences flow from the structure of that geometry, in particular from the way time and space enter the interval with opposite signs. This unified picture is more than a mathematical convenience. It represents a genuine shift in how we must understand reality. We are accustomed to thinking of space as the arena in which things exist, and time as the separate flow in which things change. The framework tells us that this separation is not fundamental. Space and time are aspects of a single 4-dimensional spacetime, and the division into space and time is something each observer does for themselves, a matter of perspective rather than a feature of reality. What is real, what all observers share, is the spacetime and the intervals within it. The flow of time and the extent of space taken separately are the slices varying with the observer, while spacetime and its intervals are the loaf, the same for all. This is one of the most profound reconceptions of reality in the history of thought, the merging of space and time into a single unified structure with a definite geometry of its own. And it is exactly this unified structure that allows us to ask with precision what happens to the carried time of a beam of light. We now have the tool we need. The spacetime interval, with its subtraction of spatial separation against temporal separation, gives the carried time accumulated along any path through spacetime. To find out how much carried time a beam of light accumulates as it travels from one event to another, we simply apply this tool to light's path. We take the spatial separation between the start and end of the light's journey and the temporal separation, and we combine them with the characteristic subtraction to find the interval, which gives the carried time. The answer for light is special, dictated by the one fact we have held onto throughout: the constancy of light's speed. When we compute the interval for a beam of light traveling between two events, something remarkable happens, something that follows directly from the fact that light always travels at exactly the speed that makes the spatial and temporal separations balance perfectly in the subtraction. What does the spacetime interval reveal when we apply it to the path of light itself? When we apply the spacetime interval to the path of a beam of light, the result is unlike the result for any object with mass, and it follows directly from the constancy of light's speed. Recall that the interval combines spatial separation and temporal separation with a subtraction, the spatial part working against the temporal part. For a beam of light traveling between two events, the spatial separation and the temporal separation are related in a very particular way, because light covers spatial distance at exactly its fixed speed. In the time between the two events, the light travels a spatial distance equal to its speed multiplied by that time. This means the spatial separation and the temporal separation for a light beam are exactly matched, locked together by the speed of light in just the proportion that makes them cancel completely in the subtraction that defines the interval. The consequence is striking. For a beam of light, the spatial separation between the start and end of its journey, when combined with the temporal separation through the characteristic subtraction, yields exactly zero. The two contributions cancel each other out completely. The interval along the path of a light beam is zero, no matter how far the light travels or how long it takes by an outside observer's reckoning. A beam of light crossing a room and a beam of light crossing the galaxy both have an interval of zero along their paths. This is not an approximation or a near cancellation. It is exact, and it is exact precisely because light travels at exactly the speed that makes the spatial and temporal separations balance. The speed of light is, in a sense, the speed at which the spatial and temporal parts of the interval perfectly offset one another. Anything traveling at that speed traces a path through spacetime with zero interval, a path that the framework calls light-like or null because the interval along it is null, vanishing, nothing. Now, recall what the interval represents along a path. The interval gives the carried time accumulated along that path, the time measured by a clock traveling the path, the object's own time. For a path with a non-zero interval, there is some carried time, some amount of the object's own time that elapses along the journey. But for the path of a light beam, the interval is zero, which means the carried time along that path is zero. A beam of light, traveling from one event to another, accumulates no carried time along its journey. If we could attach a clock to the light beam, a clock traveling along with it, that clock would register no elapsed time at all between the start of the journey and its end. The hands would not move, the count would not advance. From the start of the light's journey to its finish, no time, in the sense of the light's own carried time, would pass. This is the central conclusion toward which everything has been building, and it deserves to be stated plainly and absorbed fully. From the perspective of light itself, if we can speak of such a perspective at all, no time elapses during its journey. The light leaves its source and arrives at its destination with zero carried time in between. The departure and the arrival, separated by what an outside observer measures as a long span of time and a great distance in space, are, along the light's own path, separated by no time whatsoever. For the light, in this precise sense, the moment of emission and the moment of absorption are not separated by any interval at all. They are, as measured by the light's own non-existent clock, simultaneous, the same instant. We can see how this conclusion is the natural limit of everything we established about objects approaching the speed of light. We saw that as an object's speed increases toward that of light, its carried time, the time it accumulates along its path, decreases, with a fast object accumulating less carried time than a slow one between the same events. We saw that this reduction grows more severe as the speed approaches that of light, with the carried time heading toward zero as the speed nears its limit. Light, traveling exactly at that limiting speed, sits at the endpoint of this trend, accumulating exactly zero carried time. The trend we extrapolated earlier is confirmed exactly by the calculation of the interval. There is no carried time for light, because light travels at precisely the speed that empties the interval of any temporal content, leaving the spatial and temporal parts to cancel completely. We can also connect this to the other effects we discussed, the dilation of time and the contraction of distance, pushed to their limits. From the perspective of an outside observer, the light beam is moving at the speed of light, and the trend of time dilation says that a clock moving at that speed would be infinitely dilated. Its ticks stretch to infinite duration, its time frozen entirely from the outside. The outside observer would say the light's clock, if it had one, is completely stopped, not ticking at all. And from the light's own perspective, the contraction of distance pushed to its limit says that the distance the light traverses, however great by an outside reckoning, is contracted to nothing, so that the light crosses zero distance. The light's journey, from its own perspective, covers no distance and takes no time. The start and the end of its journey are, for the light, the same point and the same moment. These limiting forms of time dilation and length contraction agree perfectly with the calculation of the zero interval. They are different ways of seeing the same fundamental fact, that light traces a null path through spacetime, accumulating no carried time, and in its own frame, crossing no distance. It is worth being careful and precise about what this does and does not mean, because the conclusion is so easily misstated or overdramatized. It does not mean that light arrives instantly from the outside observer's perspective. From our perspective, light absolutely takes time to travel. Sunlight takes several minutes to reach us, and starlight takes years or millennia. The journey has a definite duration as we measure it, and a definite distance, and light covers that distance at its fixed, finite speed, not infinitely fast. The timelessness of light is not a claim about how long light's journey takes from the outside. It is a claim about the carried time along the light's own path, the time that the light itself would accumulate, which is zero. These are two entirely different quantities. The journey takes time from the outside while accumulating no time along the light's own path, and there is no contradiction in this because outside time and carried time are different things, the one measured by the observer's clock and the other measured along the path itself. This distinction is the same one that let us understand the particle from the upper atmosphere, which crossed the atmosphere in a stretched lifespan as we measured it, but in a contracted distance as it measured things. The carried time and the outside time can differ, sometimes dramatically. For ordinary slow objects, they are nearly the same, which is why we never notice the difference in daily life. For fast objects, they differ noticeably. And for light, they differ in the most extreme possible way, with the outside time being substantial while the carried time is exactly zero. The light's journey is long and slow from one point of view and instantaneous, indeed durationless from another, with both descriptions referring to the same physical journey and disagreeing only because they measure different things. There is one more subtlety lurking here, one that we have been glossing over by speaking loosely of the light's perspective and the light's own clock. The framework, the same framework that gives us this beautiful zero interval result, also tells us something uncomfortable about the very idea of light having a perspective. It tells us, in fact, that there is no valid perspective from which to view the world as a beam of light. The reference frame of light, the point of view that travels along with the beam, is not merely difficult to occupy, but actually forbidden by the structure of the theory, ruled out as inconsistent. We have been speaking of light's carried time as zero, and of light's own journey covering no distance, while at the same time, the framework insists that we cannot legitimately adopt light's point of view at all. This is not a contradiction so much as a deep tension, a place where our intuitive way of talking runs ahead of what the physics actually permits. Why does the very theory that tells us light accumulates no time also forbid us from ever sitting in light's frame to see the world from its point of view? The prohibition is precise and absolute, and it follows from the very principles we used to derive everything else. The entire framework is built upon observers who measure space and time, and these observers occupy reference frames, points of view from which the world can be described. A reference frame is, in essence, a way of assigning positions and times to events, a coordinate system carried by an observer. We can construct the reference frame of any observer, moving at any speed less than that of light, and from within that frame, describe how the rest of the world looks. We can ask how a fast-moving traveler measures distances and times, and the framework gives consistent answers. But when we try to construct the reference frame of a beam of light, an observer traveling at exactly the speed of light, the whole construction collapses. The mathematics that smoothly handles every speed below that of light breaks down completely at light speed, producing not strange but consistent answers, but no answers at all, or answers that are nonsensical, division by zero, infinities that cannot be tamed. The reason for this collapse traces back to the factor that governs time dilation and length contraction, the factor that grows as speed increases. We saw that this factor climbs toward infinity as the speed approaches that of light, so that the time dilation and length contraction become extreme but remain finite for any speed below light's. At exactly the speed of light, this factor becomes infinite, and the transformations that relate one observer's measurements to another's involve this infinite factor in ways that render them meaningless. Lengths would contract to exactly zero, time dilation would be exactly infinite, and the relationships between different events that the framework relies upon would dissolve into indeterminate forms. The construction that works for every speed approaching that of light fails to extend to light speed itself, not by giving a strange result, but by giving no coherent result at all. The frame of light is a singular point, a place where the structure that organizes all other frames simply does not reach. This is why physicists are careful to say that there is no reference frame for light, that light has no rest frame, that one cannot adopt the point of view of a photon. It is not a matter of practical difficulty, of light being too fast to ride along with. It is a matter of fundamental inconsistency. The framework that describes everything moving slower than light cannot be stretched to include light's own perspective, because at light speed, the framework's own machinery breaks. There is, within the theory, no valid vantage point that travels along with a beam of light, no consistent way to ask how the world looks from the photon's point of view. The question, posed within the framework, has no answer, because the framework refuses to define the frame in which the question would be asked. This puts the conclusion we reached about light's carried time in a more delicate light. We said that light accumulates zero carried time along its path, that its own clock would register no elapsed time. But strictly speaking, light has no clock, because it has no rest frame in which such a clock could sit. The carried time we computed is the limit of the carried time of objects moving slower than light, a limit that approaches zero as the speed approaches that of light. We can compute this limit, and it is unambiguously zero, but we should understand it as a statement about the limit of slower than light objects, rather than as a description of an actual experience from within an actual light frame. The interval along the light's path is genuinely zero. That is a frame-independent fact that all valid observers agree upon. But the leap from a zero interval to a clock that reads zero, to a perspective in which no time passes, involves importing the idea of light's own frame, which the framework does not actually permit. The zero interval is solid. The phrase from light's perspective is a convenient figure of speech that the physics does not strictly underwrite. So we are left in an interesting position. We have a perfectly well-defined, observer-independent fact that the spacetime interval along any path of light is exactly zero. Every valid observer, no matter how they move, agrees that the interval along a light beam's path is zero. This is not in dispute and not frame-dependent. What is problematic is the further step of interpreting this zero interval as light experiencing no time, because experiencing implies a perspective, a frame, a point of view, and that is exactly what light does not have. The zero interval is real and meaningful. The experience of zero time is a description we project onto light by imagining ourselves riding along with it, and imagining that the framework rules out. There is a way to make peace with this by recognizing that the limit itself is the meaningful content. We can take a sequence of observers moving faster and faster, approaching but never reaching the speed of light. Each of these observers is perfectly valid with a well-defined frame. As we consider observers closer and closer to light speed, the carried time along their paths between two fixed events shrinks towards zero, and the distances they measure shrink as well, and the time dilation we attribute to them grows toward infinity. The behavior of light is the limit of this sequence, the destination that the sequence approaches without any member of the sequence ever arriving. Light's zero carried time is the limit of the diminishing carried times of these ever faster observers. In this sense, the statement that light experiences no time is shorthand for the statement that the carried time approaches zero as we approach light speed, a limit that light, traveling exactly at that speed, embodies. The limit is well-defined and meaningful, even though the endpoint frame, light's own frame, is not. This careful framing matters because it keeps us honest about what the physics actually says. It is tempting to make grand pronouncements about light experiencing the entire history of the universe in a single instant, about photons for which the beginning and end of time are the same moment, about light being in some sense eternal or outside of time. These statements have a kernel of truth rooted in the genuine fact of the zero interval, but they overreach by attributing experience and perspective to something that the framework says cannot have either. The discipline statement is narrower and more defensible. The interval along light's path is zero. The carried time of objects approaching light speed approaches zero. Light has no valid rest frame, so light does not strictly have a perspective from which to experience anything. These statements are precise, and they capture what the physics genuinely establishes without the embellishments that the physics does not support. And yet the embellishments persist in popular accounts and in the imagination because the underlying fact is so striking that it seems to demand interpretation. A zero interval is a remarkable thing. It says that the start and end of a light beam's journey, however far apart in space and time as we measure them, are connected by a path along which space and time perfectly cancel, a path of no length in the deepest sense the framework offers. Whatever we make of the question of light's experience, the geometric fact remains that light traces these special null paths through spacetime, paths along which the interval vanishes, paths fundamentally different from those available to anything with mass. The light's path is a kind of boundary, a knife edge between the paths that accumulate time and the paths that would require imaginary, impossible separations. What makes light alone able to trace these special paths? And why is it that light, and only things like light, must always travel at exactly this boundary speed, never faster and never slower? The answer to why light must always travel at exactly this speed, never faster and never slower, comes down to a single property, the property of having no mass. Light is massless, and being massless is not an incidental feature, but the precise reason light travels at the speed it does, the reason it cannot slow down or speed up, the reason it traces those special null paths through spacetime. To understand this, we have to understand the relationship between mass, energy, motion, and speed that the framework establishes, a relationship that divides everything in the universe into two sharply distinct categories with very different behaviors. Everything that has mass, every particle of matter, every object built from such particles, every person and planet and star, shares a set of properties that follow from having mass. Things with mass always travel slower than light. They can be sped up toward light speed by adding energy. But as we saw, the energy required grows without bound as the speed approaches that of light, so they can never actually reach it. Things with mass can also be slowed down, brought to rest, made to sit still relative to some observer. A massive object has a rest frame, a perspective in which it is not moving, in which it simply sits and ages, accumulating carried time at the maximum rate. For a massive object at rest, all of its existence is, in a sense, motion through time alone, with no motion through space. As it begins to move through space, some of that motion through time is, loosely speaking, traded for motion through space, which is why moving clocks run slow. There is a fixed budget, and motion through space comes at the cost of motion through time. A massive object can apportion this budget in many ways, moving slowly and aging quickly, or moving quickly and aging slowly, but it always retains some motion through time, always accumulates some carried time, because it can never use the entire budget on spatial motion. To do so would require reaching light speed, which mass forbids. Light, having no mass, lives entirely outside this scheme. A massless entity does not have the option of moving slowly or sitting at rest. It cannot be brought to rest, cannot have a rest frame, cannot sit still relative to any observer. The same property that prevents massive objects from reaching light speed prevents massless light from traveling at any speed other than light speed. Light cannot slow down. A beam of light in empty space always travels at exactly its fixed speed, never faster, never slower, and crucially, never at rest. There is no such thing as a stationary beam of light, a photon sitting still. The moment light exists, it travels at light speed, and it continues at that speed until it is absorbed. This is forced by its masslessness. A massless entity has no choice in the matter. It must use the entire budget on motion through space, leaving nothing for motion through time, which is exactly why its carried time is zero. The massless thing pours all of its existence into crossing space and retains none for advancing through time. The fixed budget that a massive object can split between space and time is, for light, spent entirely on space, and so light traces those null paths along which no carried time accumulates. This gives us a deeper way to understand the zero interval and the absence of carried time. It is not that light happens to travel fast enough to empty its interval of temporal content. It is that light, being massless, has no alternative. The speed of light is the speed that massless things must travel, and that speed is precisely the one that produces null paths and zero carried time. The connection runs in both directions. Masslessness compels travel at light speed, and travel at light speed produces zero carried time, so masslessness and timelessness are intimately linked. Anything massless is timeless in this sense, tracing null paths and accumulating no carried time, while anything with mass is bound to accumulate carried time and to travel slower than light. The two categories, massive and massless, are separated by an unbridgeable gulf. A massive object cannot be accelerated to join the massless ones at light speed, and a massless entity cannot be slowed to join the massive ones at lesser speeds. The boundary speed, light speed, is the dividing line, occupied exclusively by massless things and approached but never reached by everything with mass. Light is not the only massless entity, though it is the most familiar. Any particle without mass would behave the same way, traveling at exactly light speed, accumulating no carried time, tracing null paths through spacetime. The speed we call the speed of light is more accurately understood as the speed of massless things in general, the speed that the structure of spacetime assigns to anything that has no mass. Light just happens to be the most common and most directly observed massless phenomenon, and so the speed bears its name, but the speed is really a property of spacetime itself, the speed at which the spatial and temporal parts of the interval balance, the speed that massless entities are compelled to travel. Were there no light at all, the speed would still exist as a feature of the universe's structure, the dividing line between the massive and the massless, the speed of causation and of any massless influence. This also illuminates why the speed of light functions as the universe's ultimate speed limit, not merely for light, but for everything. We have spoken of light's speed as a barrier that massive objects cannot reach, but its role is broader than that. It is the maximum speed at which any influence, any signal, any cause can propagate to produce an effect. Nothing that carries information or energy or causal influence can travel faster than this speed. The reason is bound up with the structure of spacetime and the relativity of simultaneity. If anything could travel faster than light, it could, in some observer's frame, arrive before it departed, producing effects before their causes, unraveling the orderly relationship between cause and effect that the universe maintains. The speed of light is the speed that protects this order, the maximum pace at which the universe allows cause to reach effect. It is woven into the causal structure of reality, the boundary that keeps causes before their effects for all observers. And it is the same speed that massless things travel and that empties the interval of carried time. All of these roles, the speed of light, the speed of massless things, the maximum speed of causation, the speed that produces null paths, are one and the same speed, unified by the geometry of spacetime. So light's timelessness is not an isolated curiosity, but a consequence of its place in this deep structure. Light is massless, and so it travels at the boundary speed, and so it traces null paths, and so it accumulates no carried time, and so it sits exactly at the dividing line that separates the massive from the massless, and that bounds the propagation of cause and effect throughout the universe. Every part of this is connected to every other part, all flowing from the unified geometry of spacetime and the special status of the speed that massless things must travel. The timelessness of light is the timelessness of anything that travels at this speed, which is anything without mass, which is anything compelled to spend its entire existence crossing space with none left over for advancing through time. Now we can take this understanding and apply it to the grandest scales, to the light that crosses not rooms or even the distance from the sun, but the vast gulfs between galaxies, light that has been traveling for nearly the entire history of the universe before reaching our instruments. For such light, the gap between what we measure of its journey and what its own vanishing clock would register becomes as extreme as it can possibly be, and the implications stretch our understanding of the cosmos and our place within it. What does it mean that light reaching us from the most distant galaxies has, by its own accounting, completed its journey in no time at all, even as that same journey has, by our accounting, spanned billions of years? Consider the light arriving at our telescopes from a galaxy near the edge of the observable universe. This light has been traveling through space for an immense span of time, by our reckoning, on the order of billions of years. It left its source when the universe was young, long before the Earth or the Sun existed, long before our galaxy had taken its present form. Across that enormous stretch of time, the light has crossed an almost inconceivable expanse of space, traversing the gulfs between galaxies, passing through regions of near-perfect emptiness, all the while traveling at its fixed speed. When it finally reaches our instruments and is captured and recorded, we are seeing that distant galaxy not as it is now, but as it was when the light departed, billions of years in the past. The image we capture is ancient, a snapshot of a bygone era, carried to us by light that has been in transit since the early ages of the cosmos. That is the journey as we measure it, a journey of billions of years across billions of light years of space. But along the light's own path, the interval is zero, just as it is for a beam of light crossing a room. The carried time accumulated by this ancient light, the time its own non-existent clock would register, is zero. From the start of its journey in the early universe to its end in our telescope, no carried time has elapsed. The departure and the arrival, separated by billions of years and billions of light years as we measure them, are connected by a null path along which space and time perfectly cancel. The light that has, by our accounting, spent nearly the age of the universe crossing the cosmos has, by its own accounting, crossed it in no time at all. The two descriptions refer to the same physical journey and disagree as profoundly as it is possible to disagree, the one spanning the age of the universe and the other vanishing to nothing. This is the same conclusion we reached for light crossing a room, scaled up to the largest distances and longest times the universe contains, and the scaling up makes the strangeness vivid in a way the room-sized example cannot. For light crossing a room, the difference between the outside time and the zero carried time is small enough to seem like a technicality, a matter of a tiny fraction of a second against zero. But for light crossing the observable universe, the difference is between billions of years and zero, the longest journeys the cosmos permits set against no journey at all. The light that left a distant galaxy in the early universe and arrives at our instruments today has, from the perspective the framework forbids us from fully adopting, made the entire trip in a single instant, the moment of its emission and the moment of its absorption being, along its path, the same moment, despite billions of years separating them in our frame. We must apply here the same care we developed earlier, distinguishing the solid geometric fact from the tempting overinterpretation. The solid fact is that the space-time interval along this ancient light's path is exactly zero, a fact all valid observers agree upon. The tempting overinterpretation is to say that the light experienced its billion-year journey as instantaneous, that for the photon, no time passed between the young universe and the present day. This overinterpretation again imports light's forbidden frame, treating the photon as a thing with a perspective that experiences the journey as instantaneous. The discipline statement is that the interval is zero, that the carried time of objects approaching light speed along this path approaches zero, and that light, traveling exactly at light speed, traces a null path with zero interval. Whether this amounts to the light experiencing the journey as instantaneous is a question the physics does not strictly answer, because the physics denies light the frame in which such experience could occur. The geometric fact stands. The experiential interpretation reaches beyond what the framework licenses. There is an additional complication that the cosmic scale introduces, one we have set aside until now. On the largest scales, the universe is expanding. The space between distant galaxies is growing, stretching, carrying galaxies apart from one another over cosmic time. This expansion affects the light traveling across the cosmos in important ways, stretching its wavelength as it travels, shifting it toward the red end of the spectrum, which is how we know the universe is expanding in the first place. The expansion also complicates the simple picture of distances and times, because the distance the light has traveled is not fixed, but has grown during the journey, as the space the light crosses expands beneath it. The full description of light's journey across an expanding universe requires the broader theory that handles gravity and the large-scale structure of spacetime, a theory that extends the framework we have been discussing to include curved and dynamic spacetime. The details become more involved, and some of the simple statements about distances and times require careful qualification on these scales. But the central conclusion survives the complication. Even in the expanding universe, light travels along null paths, paths along which the spacetime interval is zero, paths that accumulate no carried time. The expansion stretches the light and complicates the bookkeeping of distances, but it does not change the fundamental fact that light's path through spacetime is a null path with zero interval. The light from the most distant galaxies, having crossed an expanding universe over billions of years of cosmic time, still traces a null path, still accumulates zero carried time along its journey. The expansion adds richness and complication to the story, the redshift, the growing distances, the dynamic spacetime. But at the heart of it, light remains timeless in the precise sense we have established, tracing null paths along which no carried time accumulates. This casts the night sky in a particular light. When we look out at the stars and galaxies, we are seeing light that has traveled to us across space and time, light from sources at many different distances, and so light that left its sources at many different times in the past. The nearby stars we see as they were years ago, the more distant ones as they were centuries or millennia ago, and the faraway galaxies as they were millions or billions of years ago. The night sky is not a snapshot of the universe as it is now, but a layered composite of many different epochs, each point of light showing its source at the time that light departed. We are looking into the past whenever we look out into space, and the deeper we look, the further back in time we see. And every photon delivering these images, from the nearest star to the most distant galaxy, has traced a null path to reach us, accumulating no carried time, arriving with its own clock were it to have one, reading exactly zero, regardless of whether its journey took years or eons by our reckoning. There is something worth pausing on in this picture, a way that light's timelessness connects to its role as the carrier of information across the cosmos. Light is how the universe communicates with itself across vast distances, how distant events become known to distant observers, how the light of an ancient star eventually reaches an eye or an instrument far away in space and time. And the carrier of all this information, the light itself, makes its journeys along paths of zero interval, connecting widely separated events through null paths along which space and time cancel. The web of light that crisscrosses the universe, linking emissions to absorptions across all distances and all epochs, is a web of null paths, each one a connection along which no carried time elapses. This web is intimately related to the causal structure of the universe, the network of what can affect what, which is itself defined by the paths that light can take. How does light's special speed and the null paths it traces define the very limits of cause and effect throughout the cosmos?